Okay, next we're going to speak about routing protocol security, because as we spoke when we defined the planes of a network device, in the control plane, the router has two main set of, let's say, protocols. It has traffic, it has routing protocol traffic and ARP traffic. That's the most important two types of protocols the router has in the control plane part when it does just IPv4 unicast routing. If you add MPLS, it is also LDP and BGP, of course. If you add IPv6, it also has IPv6 traffic. But in a regular basic IPv4 router in there, the main two protocols which are control plane protocols are going to be the routing protocol and the ARP for IP to MAC resolution. So routing protocol security. Three main actions need to be taken to secure a routing protocol, or can be taken. Something which is called prefix limit, route filtering, and authentication of the protocol, which optionally can also include encryption. But in general, you're going to do only authentication, because very few protocols also support encryption of the routing protocol packets. Now, the routing protocol prefix limit, what it does, as the name states, it limits the number of prefixes learned by that routing protocol. It's applied at the database level of the protocol, and of course, as a result, it limits per protocol RIB entries. What is the scope of this feature? Is to prevent a routing protocol from being overloaded. Like, for example, you can imagine that IGPs like EIGRP or OSPF or even ISIs, but let's say EIGRP or RIP or OSPF, have not been designed to be able to sustain hundreds of thousands of entries in the database. So the prefix limit, I said in there that it's meant to prevent routing protocol from being overloaded, because I don't want somebody to accidentally redistribute the BGP internet routing table into EIGRP fully, or into OSPF or into RIP, because those protocols are not designed. They cannot actually, they're going to crash pretty much. They cannot keep up with such amount of prefixes in the database. So we limit the number of prefixes that that a protocol can have in the database in order to prevent the routing protocol from being overloaded, and of course in order to prevent Ceph memory exhaustion, causing router to do process switching for transit packets. What I mean by this is the following. If, let's say, a router pick protocol number A, let's say. Okay, let's pick protocol number A. Let's pick BGP. And if you don't put a limit of the number of prefixes that BGP can learn in the database, let's say BGP learns 1 million routes. Okay, it means that BGP is going to send all of those routes. So what happens? Let me actually make this more visual in here. This is my router. And again, ideally, to understand me completely, you need good RNS knowledge. Because what happens is the following. In here, I'm going to have protocol database, whatever the routing protocol database, which is going to contain all information learned about that protocol, from that protocol, routing protocol database. So it's going to contain all information learned about that protocol from their neighbors or locally injected on that router. Because in the database of RIP, for example, or EIGRP, we put what we learn from our EIGRP neighbors and also what we locally inject on that router in the database. Now what happens is that the best entries from the database for each prefix is going to be sent to the routing protocol, what is called local RIB. Some protocols have a command to show the local rib, some of them don't have the command, but all of them function the same way. Like for example, if the protocol is EIGRP and it has two paths for the same destination, it's going to choose one path, one best path based on EIGRP criteria. It's going to send that best path to the EIGRP local rib. And then from the local, so the best paths are being sent to the local rib, the best paths. And all of those best paths are being sent to the global rib, which controls the process which controls the show IP route. What ends up what ends up being installed in the routing table. So you can imagine, for example, if the protocol is BGP, and in a database I have 1 million routes, 1 million entries. We may say that's an unfeasible number, but we're reaching that number. We can take not 1 million, we can take, let's say, 10,000 entries. Those entries end up in that protocol's local rib, and if the router doesn't have any other information for those destinations via other routing protocols, they're going to end up also in the rib. So I'm going to end up in the rib with 10,000 routing entries. Now each router, to do process switching, it means that it's going to install the rib entries, the routing table entries, in the fib. Because to be able to do Ceph switching, it means I don't go and ask the router how to route a packet, but the routing table is pre-populated in the fib, which means in the ASICs at the hardware level. And you can imagine that the ASICs have a limit. So the ASICs, it's a computer chip which has a limited amount of entries it can sustain. So what happens is that based on the router model or on the line card model, it can happen that the router can receive more entries from the rib than actually fib can support. So if you can install in the fib only 5,000 entries and the rib wants to install in there 10,000 entries, the router cannot do that. So what's going to happen is that the router is going to change over completely to process switching. So all packets will be at that point process switched because we have a Ceph exception in the ASICs. We cannot put in the ASICs what we want to put in there. And that actually happened a couple of years ago when it was a completely blackout on the internet. Because most of the ISPs, they have a couple of Catalyst 6K switches, Cisco switches in their networks. And what happened is that the ASICs, most old ASICs of those Catalyst 6K switches had the ASIC limit to be 512,000 routes. So what happened is that when the BGP routing table exceeded that number, we exceeded the number of routes supported in the ASICs. And then what happened? The routers, everything blowed off because all routers, all of those 6K switches went to process switching. And you can imagine that a router can, the power of a router that he can forward terabits per second is not the power of the CPU, it's the hardware power. So it's not the brain power, but it's the muscles, the ASICs. So if the ASICs are not usable, the router is going to fall down from 100 terabits per second forwarding packets is going to fall down to 55 megs per second or whatever. There was a complete blackout on the internet a couple of years ago for this reason, and of course a lot of clients also encountered this problem because of this reason. So you want to limit the number of prefixes that a router can put in the database. As I said, to also make sure that the protocol actually can sustain that number, and also to make sure that the Ceph memory is not overloaded, which means it's going to cause the router to do process switching for all transit packets, which means at that point is pretty bad. Route filtering, it means that we restrict now not how many prefixes, but which prefixes can be learned by a routing protocol. So route filtering has to do with filtering what prefixes or what routing updates can you accept from your routing protocol neighbors. So because it's going to be likewise, this filter applies at the database of the protocol. So I'm going to filter not to receive, for example, via rep a route for 10.10.10.0/24. Because rep is going to filter that route out, it means it's also not going to go into the rep because it's filtered at the protocol level. The protocol cannot send that route to the rep in there. So likewise, it prevents routing protocol from being overloaded, and also it prevents erroneous prefix advertisements. Like for example, imagine that in this case in here we have on the left side is company A, let's say, client A, company A, and on the right side is company B. So two different enterprises. Company B runs EIGRP internally. Company A runs OSPF internally. And this is our border device, let's say, in there. The ASA is connected to both enterprise A and B, which means ASA has to do redistribution back and forward between OSPF and EIGRP. And now let's speak from enterprise B point of view. Let's assume that enterprise B has in its network only IP addressing in the range of 10.00/8. And when you do this distribution on ASA3 between OSPF and EIGRP, you knew initially that client A had in its network prefixes in the range of 192.168.100/16. So there was no IP addressing overlapping to begin with. But of course, it can happen that at some point somebody comes in company A and they forget about this point of distribution and they add a new subnet of 10.10.10 to be used for whatever reason, 10.10.10.0/24. Which means router 3 is going to advertise this information via OSPF to ASA3, which is not good clearly, because at this point ASA3 learns about a network which is contained. So ASA3 belongs to customer B. So at this point ASA3 learns about an internal network of 10.10.10.0/24, learns about that network from an external domain, from enterprise A. So clearly that's not good, because at that point, depending how ASA3 is configured, it may prefer the OSPF path or the EIGRP path. So that's not good clearly. So this is what I said, that route filtering also prevents erroneous prefix advertisements. So when you have a border device, border router, which performs distribution back and forward, you ideally gotta make sure that from the untrusted routing domain, not the internal one, you do inbound filtering to make sure you don't receive from that domain prefixes which you also own internally in your network, because that screams for trouble in there. Now, routing protocol authentication enforces routing protocol packets to be authenticated, all routing protocol packets. So this is a security feature used to prevent spoofed routing protocol packets. Now, for example, if we run EIGRP in here in AS100, somebody could also connect, like in here in VLAN 31, an attacker, and start sending EIGRP packets to both router 3 and router 1, possibly from spoofing the source. So the attacker is going to send an EIGRP packet to router 1, but that EIGRP packet is going to have a source of router 3, and of course destination of the multicast group of EIGRP. So the attacker spoofs the source of the EIGRP packet to behave like that the EIGRP packet came from router 3. And you can imagine that at this point, the attacker can influence router 1's routing table because router 1 has an adjacency with router 3, EIGRP wise. So when router 1 receives an EIGRP packet from router 3, it is going to accept it and use it. So clearly this is not good. So we want to make sure that this attacker cannot inject spoofed packets, which means we're going to make EIGRP to be authenticated. Because at that point, the attacker also needs to know the authentication keys or key in order to actually send spoofed and erroneous EIGRP packets. Authentication options, all protocols are going to support either clear text authentication or HMAC authentication via MD5 or SHA. First of all, clearly clear text authentication doesn't really add a lot of security, so it should not be used anymore, ideally. Because, for example, why is that not good? Because clear text authentication means that I'm going to send in the routing protocol packet the password in clear text. So for example, if I enable between router 1 and router 3 clear text authentication with a password of XYZ, it means that in the protocol packets in the updates sent between 1 and 3, they're going to send that password in clear text. So it means that if the attacker is connected, like router 1 and 3 are connected via a switch, via a layer 2 switch, and also the attacker is connected to that switch, the attacker. Because mostly, in general, the running protocol packets, IGP-wise, are multicast. It could happen that, of course, depending on a lot of other configurations, but to keep it simple is that when router 3 sends a EIGRP multicast packet, the switch receives it, and if the switch is misconfigured depending on the switch type, because it's a multicast packet, the switch may send the packet out to both router 1 and to the attacker. So then the attacker receives the packet from router 3, sees the clear text password, so then it can perform the same attack again. While this is not possible if you use a HMAC based authentication, because HMAC is going to send the authentication, the password not in clear text but as a hash. And MD5 and SHA are hashing algorithms, just to make sure everybody is on the same side, not encryption algorithms. Now from the authentication point of view, REAP version 2 supports both clear text and MD5. OSPF supports clear text, MD5 and SHA-2 authentication. EIGRP supports MD5 authentication and SHA-2 as well, but in the newer codes. So let me just put it in there. So depending on the code type you're running, it also supports SHA-2. And BGP supports only MD5 authentication, but via TCP option 19, because BGP doesn't run on top of IP, runs on top of TCP. The IGPs, OSPF and EIGRP, run on top of IP directly. They have their own protocol numbers, so they're going to make use of their own built-in authentication methods, while BGP, because it runs on top of TCP, it makes use of TCP option 19 for that purpose. Now for the CCNP exam, we're going to do one kind of configuration. We're going to do EIGRP authentication. We're going to configure this on both iOS and ASA. So the steps on iOS is just to configure globally a keychain, and in the keychain you can define one or multiple keys, and for each key you define the key string and the lifetime. So iOS uses keychain for EIGRP authentication to allow for transparent and fast key transition. Because imagine that a correct security policy would be that you periodically change the keys in there, because you don't want somebody to which has access to the router to leak the keys to some attackers, and then the attackers can, of course, as long as they know the keys, it's like there's no authentication in place. So ideally you would want the keys to change periodically, which means for each key in the keychain you define clearly the key string and the lifetime to allow for automatic key rotation. Then you enable authentication at the interface level, and then also at the interface level you tell which keychain to be used by EIGRP. At the ASA it's simpler because the ASA doesn't use keychains. You just enable authentication at the interface level for EIGRP, and then at the interface level you configure the key number and the key string in there. And of course, because both the key number and the key string are used as seed values in the hashing computation, both of them have to match in order for authentication to work. So between two devices performing EIGRP authentication, I'm going to do it via MD5 in this code because it only supports MD5, my code. Then because that's the case, you have to make sure that both the key number and the key string are in a perfect match between the devices, otherwise authentication is going to fail. Now verification, on the iOS you verify the keychain, show keychain. You verify EIGRP authentication with show IP EIGRP interfaces detail if you speak about IPv4 EIGRP. And on the SA it's going to be show EIGRP interfaces detail to verify if authentication is enabled or not. Now let's go to the implementation part. So between router 3 and ASA3 in here, we're going to perform EIGRP authentication between router 3 and ASA3. I'm going to use a key number of, let's say, 10 and a key string of EIGRP. Let's follow up on those steps. Router 3. So keychain, EIGRP authentication. Make sure you use only capitals or smalls, otherwise the screen's for typos. Authentication. Then key number, I said 10, and key string EIGRP. If I don't define any lifetimes, it's going to be indefinitely, like it's never going to expire. Then we go at the interface level facing ASA3, which is going to be FA0038. And we say IP EIGRP, the IP authentication mode, EIGRP 100 MD5. And IP authentication, as you can see, all neighbors went down in there. So actually I have, because router 3 has two neighbors, ASA3 and router 2, I would have to do the authentication on router 2 and ASA3 in the end. Because on this segment, router 3 has two EIGRP neighbors. And you cannot, because authentication is enabled at the interface level, it means you cannot configure per neighbor authentication. Which means because router 3 has two neighbors out there, we have to authenticate both of them, or none of them. So IP authentication keychain, EIGRP 100, and the name of the keychain, which was EIGRP authentication. We copy paste the keychain also on router 2, show running section keychain on router 2. And then we also paste show run interface FA0038. We paste the authentication commands also on router 2's interface gig01. Membership is up again. So now we go also on the ASA3, and we go directly at the interface level, which is gig01, and we say EIGRP authentication mode EIGRP 100 MD5. So it's the same command but without the IP keyword authentication key EIGRP 100, and we define the key number authentication key EIGRP 100. We first defined the authentication key string. It was EIGRP. Let's confirm that was the key. It was EIGRP. And then we say key ID number 10. So now at this point, Vault should also become a neighborhood router with ASH2, and there we go. So show IP EIGRP neighbors interface on FA0038. I'm back again a neighbor with both ASH2 and Vault2. And if you say show IP EIGRP interfaces FA38 detail, a detail option is before the interface. It's going to show that on that interface I have authentication on of type mode MD5, and that's the keychain which is being used. Likewise on ASH2, show EIGRP, show EIGRP authentication, show EIGRP interfaces detail. It is going to be Gig01 is going to be outside. And likewise authentication MD5 key is removed for security reasons on the SA, but you see the key ID. If you want to see the key on the SA on show interface Gig01, likewise you don't see the key. So just for security reasons to prevent shoulder watching, so you gotta say more system running config and begin or include this command. And you're gonna see the key in clear text, which it is gonna be EIGRP.